Now that we understand the properties, let's discuss how formation actually happened. The only good theory we have that explains solar system formation is what we refer to as the nebular theory. When I first began teaching many years ago, we actually referred to it as the nebular hypothesis. So if you remember back to when you discussed scientific method and so on, hopefully that shows that we've gotten a lot of evidence that this is probably what actually happened. So the entire idea is that our solar system actually began within a giant nebula. If you remember back, nebulas are giant clouds of gas and dust, part of the interstellar medium, and particularly dark nebulae are ones that are cold and dense, which allows gravity to overcome pressure, which allows them to collapse and actually start beginning forming stars. The ideas that have now become the nebular theory were actually first proposed by Kant and Laplace over 200 years ago. So this is actually kind of an old idea. I mean, it's still somewhat modern. We're not talking ancient Greeks like we have in other aspects of astronomy, but it is still kind of an older idea. And we now have a lot of evidence to actually support that this is likely what actually happened. So again, we go back to the ideas of gravity versus pressure. Within a dark nebula, they have high density, which means we have great gravity, but they have low temperature, which means they have low pressure pushing out. So in this case, gravity is able to overcome pressure, and we have these pockets within the overall dark nebula that are going to be able to start collapsing under gravity. Well, as they collapse, if they are rotating at all, as they shrink, they're going to have to speed up. This is caused by conservation of angular momentum. So it's similar to what happens with a figure skater. When she starts her spin, her arms are out wide and she's rotating slowly. But as she draws her arms in, then she rotates faster and faster. So as the entire cloud gets pulled in, it's going to begin to speed up. Because it's speeding up in the one direction, it's going to stay puffed out. However, the other direction where it's not rotating, gravity is going to be able to keep pulling stuff in until we end up with a very broad but thin disk of material. Now, as the material is orbiting around, anything that has a strange or highly eccentric orbit is going to have a high chance of collision. So in this case, this blue particle will swing in close to the center and then swing back out, whereas most of the rest of the stuff is going to be on nearly circular orbits. What this means is this bluish particle is going to have a high chance of collision as it moves in. Because of that, it's going to get hit and knocked around until eventually it comes into a nice circular orbit. It's similar to what kind of happens with bumper cars. If you've ever watched kids doing bumper cars at an amusement park, at first, they're kind of chaotic, but over a while, because of the continual collisions, they all start to flow in a single direction. Now, as the material fell, it gained speed. In other words, it's converting gravitational potential energy into kinetic energy. Now, when the material falls into the disk, that kinetic energy is going to get turned into thermal energy due to friction. What this means is the regions where the material has fallen the farthest is going to end up being the hottest. This is going to be the center of the disk. So the center of the disk is going to be very hot because this material has fallen the farthest. As we go from the center out towards the edge, it's going to cool off because the material out towards the edge has not fallen as far and therefore didn't convert as much energy into heat. Now, this central hot area that has the most mass, the center of the disk, is the protosun. This is the thing that will eventually turn into the sun. The disk of material surrounding the protosun is the protoplanetary disk. This is where the planets are going to form eventually. Now, part of what has really given us evidence that this is likely how our solar system formed is by looking at new star-forming regions. So, for example, the Orion Nebula, which is an active star-forming region. As we look in these areas, we often find new stars with circumstellar disks. These disks surrounding them, which is where we believe planets are forming. Here we're looking at a close-up of two of these systems. On the left, we're looking at the system edge-on. Notice that in the center, we've actually blocked out the central star. That's because if we didn't, we wouldn't actually be able to see the disk. However, notice how thin the disk is. On the right, we're seeing what we call face-on. So it's like we're looking down on top of the disk. Again, we've blocked out the central star so we can actually make out the disk, but notice how broad that disk actually is. All right, here is a thought question for you. Why do all planets orbit in the same direction in roughly the same plane? A, it is a great cosmic coincidence. B, they all formed in the rotating protoplanetary disk. C, the sun captured them from other stars in similar processes, causing similar motions. Go ahead and think about it, and we'll talk about it in just a bit. All right, so why do all planets orbit in the same direction in roughly the same plane? It's B. They all formed in the rotating protoplanetary disk. All of the material is going around in the same direction, and the disk was really, really thin, so they're all going to form on the same plane.